Hello, folks. I'm going to show you what I need you to do for lab this week since you're not coming to class. If you scroll down to the course material for this week, you're going to be doing the same procedure as everyone in class. The only difference is I'm going to give you the data and you're going to run the computations yourself. So you won't have to physically obtain the data by any means, especially since you don't have the technology available to you to be able to do that. So in the KineticFriction Lab procedure, it goes through and discusses the forces of kinetic and static friction, how they are defined by the coefficient of frictions and the normal force, the support force acting upward. We have this figure 1. This is essentially the apparatus that you'll be using. If you can see behind me, there is a set of block of woods and then a photo gate and some masses. You're going to be students basically hang the mass from the pulley system, and the string, as the mass hanging down accelerates forward, the wooden block slides across the table and spins a pulley. The pulley has spokes which engage a time-sensitive laser that allows it to track the speed as a function of time. And so what you do is you just do 10 runs of that with 3 different orientations. The first orientation is such that you basically are, let me just put this down for a minute. You basically are allowing the block to slide like this across the table. And that is your first set of data points. And then you basically stack another block on top and let it do the same thing, slide across the table. That's your second set of data points. And your third is to allow it to slide on its edge. So we're tracking 3 different things. We're tracking how much surface area the wooden block has, how much weight it has, and also the speed of the pull. And we're seeing if the kinetic friction coefficient depends on any of those things. The reality of the situation is that it doesn't. How do we know that? Well, the surface area and the weight of the object don't really play into calculating the coefficient of friction. If you look at this equation, number 2, the only thing that weight does, the normal force, the support force, is give us a magnitude of how much frictional force is actually there. It doesn't compute mu k. Mu k is a completely independent variable in this entire study that depends on things like adhesion of the molecules between the surfaces, the structure at the microscopic level, are there ridges, are there bumps, and the material, the makeup of the material themselves, okay? So kinetic friction doesn't depend on the things we're studying today, and you should see that as we go through. The second section goes through free body diagrams, gives the equations of motion that we'll be using in the experimental setup, okay? And so as you can see, each of these free body diagrams gives us the calculations we need to determine the coefficient of kinetic friction. As you can tell, we orient positive as always. This block is hanging off the table. This isn't actually a block. This is just a mass hanger, and you can adjust the mass on there. This guy is the block. So you have kinetic friction pulling backwards. You have tension of the string pulling forward. You have the acceleration of the block forward, the normal force acting on the block, and the gravitational force. You plug those into the equations of motion, and you get an expression for tension as it relates to the block's mass and the kinetic friction coefficient. Then you do the same thing for the second block, or the mass hanger, and you get this equation, number 4, which is just the tension upward minus the gravitational force downward equals negative ma, which is Newton's second law. Okay, then what you can do is you can say, okay, solve both of those equations for tension and then set the tensions equal to one another, because the tension along the string is the same at every single point along the string, and in accordance with Newton's third law as well. And so once we get to this point, equation number 5, we just solve for mu k, and we get this expression right here. Okay, this is basically the equation you're going to use to calculate the coefficient of friction for each row of your data table that we give you. Okay, so look for the data table in the online resources for remote learners folder. This video is in there, and the procedure is very simple for you. All you have to do really is in these tables, you'll be given data on mass 1, mass 2, and the acceleration. And what you're going to do is you're going to calculate mu k using this formula right here. And I'll demonstrate how to use that towards the end of this video. So you're going to do that for the 10 runs, and then you're going to calculate the average and standard deviation. Then you're going to do it for, so that's for the friction of the block sliding like this across the table. Then you're going to do it again. You're going to have data that you're going to calculate mu k for. So you're going to get really comfortable calculating mu k. But the point is that I can't just let you get away with not doing some work this week. Then you're going to calculate the average and standard deviation. Then you're going to do it for the third one when it's on its edge. So these tables should appear in your notebook with all these calculations. And you don't have to show anything. If you want to show your calculations, you can, but really only need to see one. But you're going to have to do it by hand for every single one. So I don't know if you want to go through the labor of doing that all by hand when your calculator will work just fine, or use Excel to do it. That's fine by me. And then you're going to answer all these questions. Okay. So that's pretty much it for the procedure for you if you're at home this week. I wish I had a better option, but this is the best I can do with the resources we have. The other thing that you need to look at is, or I need to show you, is the file we're going to do to run the test. So we have a Pasco, which is a very nice interface, and it allows you to plot time versus linear speed for these runs. Let me go ahead and demonstrate. All of the settings are correct. What I can do is I can hit record, and when I spin the pulley, it begins to record data. Okay. And so what we're doing in this case is we are plotting the linear speed as a function of time. You'll notice that there's a few data points along here that just don't fit this curve very well. It looks like a nice curve from about right here to about right there. So what we can do is we can eliminate some of the data. Okay. So what I'm going to choose to do is I'm going to choose to look at where this decreases a little bit. So it's going to go from decreasing to sort of increasing. All right. And I don't want to eliminate too much data, but you'll notice that the data doesn't increase uniformly. There's actually sort of a curve to this, and that's because we're giving the spindle some acceleration. So it looks like the first data point is not a very good one because it's lower than the secondary one. So I can right click that and delete it, and then the slope adjusts accordingly. All right. This is giving me a negative slope because of the way this spindle is oriented. And that doesn't matter. You're still going to get a nice positive mu k when you do the calculation. But what you would be doing, I'd be doing 10 runs where the string is the instigator of accelerations. And this slope here is the acceleration that you put into your data table. And from there, you have m1, m2, the acceleration of gravity g, and the acceleration a equals this guy right here, 0.125. Plug that into that equation, calculate it, and you get something between 0.20 and 0.50 for your coefficient of friction. Okay? And that is measuring the friction between this wooden block and the classroom tables. So that's more or less it. Obviously, our slopes are not going to look like this because I just flicked the spindle or the pulley, but you get the idea. If this were actually a trial run, which I can do, give me just a moment to set that up. So now we're going to actually do a test run of this, see if you can see what's going on here. To the hanging mass, I've added just enough mass so that the block slides nice and uniformly across the table. If you can see it on the screen there, it's just barely getting enough acceleration to go forward. Okay, without sticking. That's the goal here. We don't want this thing to stick at all. We just want it to nice and neatly accelerate towards the pulley. Okay, so I'm going to delete this last run, and now we're going to hit record and allow this to go. Okay, and so there's a lot of data all over the place on this. As you can see, it goes up nice and linearly, and then it kind of just goes to hell. All right, and so what we want to be looking for is when does it go from accelerating nice and uniformly to in a positive fashion to all of a sudden going negative, and it looks to happen right about there. So we can actually highlight all of this data, and we can choose to exclude the values, and we get an acceleration of 2.82 meters per second, which is exactly kind of the thing we're looking for. And let me fit this to the entire curve here. Now I can also choose to get rid of this value because it doesn't really help us at all. It kind of sits outside the kind of typical data that's going on. So the actual acceleration is 2.79, which is significantly lower than the gravitational acceleration, which makes sense because this weight system is pulling a block across the table. So what we would do is we would, and I'm just going to use this for the sake of argument to make this a little bit simpler, is we'd want to basically enter in our data in our notebook with the following table. I just received an acceleration of 2.79. Oh, let me do my num log, 2.79. And then I need to measure both the mass 1 and the mass 2. I can do that easily by just checking what mass 2 is on the hanger, and I can measure M1 by using the triple beam balance. So I'm going to go ahead and do that really quickly. So I had to change the mass a little bit on the hanger because the acceleration was too great. And there was probably too much acceleration to begin with. So we have to do that run again. And so I'm just going to hit record, stop, and now I'm going to delete anything that is out of place, which is this data right here. You just have to keep doing this over and over and over again. Looks like we got a good acceleration of 1.85. So I'm going to record that, 1.85, okay? And it gives me a coefficient of friction of 0.523, all right? Because the mass of the hanger was 350 grams, the mass of the block is about 400 grams. And so really, these data points will not change at all for the rest of my runs, okay? And so the only thing that's going to change now is the amount of acceleration I achieve. And so I'm going to do this run several times, and then I'll pause the recording, and you should be able to copy the data points down. I'll also provide this Excel sheet without the calculations of μk so you can see what's going on. So here it is, folks. I did the 10 runs, and these are the results I got for the slopes on the acceleration of that block. So at this point, you have your mass 1, you have your mass 2, you have your acceleration, and all you need to do is then calculate the value of μk using the equation found on the procedure, equation number 6 here. So you'll plug in the value of M2, you'll plug in the value of M2, you'll plug in 9.8 here. The acceleration for each row will go here and here, and M1 again will go here, and G will go here, and it'll give you a nice round number for the coefficient of friction. So you'll see the same thing for the secondary table and the third table, and you're just going to record that data in your notebook and do the calculations on your own, and then answer those questions. That's it. That's all you need to do for this lab this week. Maybe in the future I'll come up with something better, but this will have to do for this week. Thanks. And that's all there is for today.